So today what we're looking at is integration. Now, integration is the opposite of derivation, meaning if we want to find the derivative of a function, integration is undoing the derivative. We're going backwards. Typically it's written in integral notation. When we see the long, almost cursive s, not cursive s, when we see the long elongated s, that means we're finding the integral of this function. Which means that typically one of the things that we have to do is we have to rewrite the powers into something that we can reverse. Because when finding the derivative, we use the powers and the coefficients to find the derivative. So we'll have to do the same thing when finding the integral when we integrate the function. The other thing that we'll likely do is we might remove coefficients or rewrite the function so that we could match it off a list of known derivatives. If I see something where I have a secant squared, I'll go down and see what trigonometric function produces a secant squared. For example, if I have something that looks like this, and I have the sine squared over the cosine squared, I might go down my list of known derivatives until I find one that says, hey, boom, if I write it as the secant tangent, I know that the secant produces the secant tangent, so therefore, boom, my integral is going to be the secant plus c. So let's go ahead and let's try a few of these. So to start out with this first one, now, when it's already written in its power form as a polynomial, we can keep a good bit of the equation. So for example, when I integrate this, I'm going to keep the negative 24x to the fifth. But what I am going to do is I'm going to say, well, hey, if I subtracted 1 from the power, if I want to go in the opposite direction, I have to add 1. Also, if I took that 6 and I multiplied it times the 24, or multiplied it times whatever that was to produce a 24, to reverse it, I'm also going to have to divide it by that 5 plus 1, which is 6. And this is going to be where we find our derivative, or not our derivative, our integral. So negative 24 divided by 6 is going to give us a negative 4x to the sixth. That is the integral, the indefinite integral. Because if we were to reverse this process and find the derivative, 6 times negative 4 is negative 24, take away 1 from the power, 5. The constant, because that is x to the 0th power, 0 is going to cancel that out, and that won't show up. So we see the fact that if we take the derivative, or if we take the integral, they're just opposite ends of the spectrum. Let's get a little bit more practice in here. Remember, we can keep most of the function. I'm going to keep the negative 6x. What I will need to write, just to help me out, is the power. That's x to the first power. So that way, when I reverse this and add to the power and divide by whatever that power was, I know what I'm going to be dividing by. It's going to be a negative 3x squared plus the unknown constant. Boom. We just integrated the indefinite integral. We have something like this. Again, we keep the power, or we keep everything that's here. So negative 24x to the fifth minus 10x to the first. We're going to add 1 to each of the powers, and we're going to divide by whatever that sum would equal. Over here I divide by 2. Over here I divide by 6. And that's going to give us negative 4x to the sixth minus 5x squared plus c. Indefinite integral. The process works the same way when we have negative exponents. Now, one of the ways that you're going to ask when we integrate this is, do I keep it in the negative, or do I put it in its final form where I'll move that x down to the bottom? This is already set up for us to integrate, so let's go ahead and just integrate this and see where it lends us to. Add 1, divide by negative 4. That's going to give me a negative x to the negative 4th. Now with this, because the problem was given to us with negative exponents, we can go ahead and we can keep this. However, if you wanted to put it in standard form, or if the problem states, please put the problem in standard form, what we could do is let's do this in orange, actually no, this is exactly equal. I could say this is a negative 1 over x to the 4th. I could also accept that as an answer. But because the original problem was given us to a negative exponent, we can put our plus c. we can put our final answer plus c as a negative exponent. So now you've seen several of those. Why don't you go ahead and try number 9, pause the video, unpause it when you're done, and see how well you did. Okay, so we remember that negative 2x to the negative 3, we keep everything that we see. And we're going to modify it as best we can. We're going to add 1 to the powers, and we're going to divide by whatever that sum is in the power. So we're going to divide by negative 2, and we're going to divide by negative 4. So in this case, we're going to get a negative x to the negative 2 and a negative 5x to the negative 4 plus c. This would be our final answer if we were allowed to list it in whatever format. Or if we wanted to list it in standard form, what we could do is say negative 1 over x squared minus 5 over x to the 4th plus c. There we go. And that's going to bring us to these problems. So let's take a look at some of these. Now what you'll notice is the fact that these are written in standard form. So we're going to want to put our answer in standard form regardless of what's going on. Now the first thing is we will actually need to rewrite these. So let's rewrite these as we include what we need. So that x to the 3rd is going to be a negative 4x negative 3 minus 8x negative 5. I'm going to go ahead and I'm going to add my 1 to the power, and I'm going to divide by whatever that sum is. And that's going to be all we need to get our answer. That's going to be a 2x negative 2 plus 2x negative 4 plus c. So my final answer is going to actually be a 2 over x squared plus 2 over x 4th plus c. There's no alternate answer because that is the only answer. When our original problem is in standard form, we give an answer in standard form. Awesome. So now let's try the next one. This one deals with a fractional exponent. Again, the same concept applies. If we're given a fractional exponent, we can give a final answer in a fractional exponent. Or we can give an answer in radical form. Most questions are going to tell you which form you want, but here, why don't you go ahead and give this a shot. Okay, so now that you've done that, let's go ahead and say I have a negative 14 thirds x to the 5 halves. I am going to add 1 to my 5 halves, and I'm going to divide it by whatever 5 halves plus 1 is. Now that plus 1 is going to be 2 halves, so I'm going to get 7 halves on the bottom there. So that way when I evaluate what's going on, I'm going to keep change flip here. I'm going to have my negative 14 thirds times 2 sevenths. And my x is just racking up some exponents here, times x to the 7 halves. Now again, we've talked about that I am going to be allowed to keep some of this. That's going to be a reduced down to a 2 and a 1. So this is going to reduce down to a negative 4 thirds x to the 7 halves plus c. Now there's the answer in the form of the question that I was given. If you wanted to put the answer in standard form or what we would call a radical form, let's see, this is going to be negative 4 thirds. I have 2, 4, 6. I have 3 x's that are going to come out, and I'm left behind with a root x. This is the answer in standard or in radical form. Awesome. So now one of the things that we're going to look at is we're going to look at some that deal with trigonometry. So with the trig functions, all we are really trying to do is we're trying to match any of our trig functions to a list of known derivatives. So I'm checking to see, hey, can I produce a cosine, a cosecant, cotangent, so that I can reverse and say, here is the integral. If I see something that looks like this, I know that the integral is going to be the reversed process. Let's go ahead and take another peek at number 15. So number 15, the first thing we're going to notice is that the cosecant cotangent, what we have is that we notice that the derivative of cotangent is going to produce a negative cosecant cotangent. So what I'm going to do is I'm going to move that 5 out of the derivative, or out of, not the derivative, out of the integral. So the 5 comes out, and I leave behind the negative cosecant cotangent dx, which we know that this, the integral or the antiderivative, is going to be that cotangent. So I have the cotangent of x, and then that 5 just kind of hangs out there. It doesn't go anywhere. And that's it. Easy enough. Trig looks like it could be harder, but really it's not. If I look at number 17, I have 2 sine of x. Again, we know that from our list of derivatives, we know that the cosine produces a derivative of negative sine. So what we're seeing here is I need to make this into a negative sign. So I'm going to pull out a, not just a 2, I'm going to pull out a negative 2. And now if I pull out a negative, I have to leave behind a negative. That way the negative times the negative will result in the positive original expression that we had. But what I'm left with is a negative sine of x dx. And that negative sine of x is what we need to make the cosine of x. And we just leave the negative 2. Nothing changes about that. It doesn't go anywhere. Perfect. And so now that you've seen a few of those, why don't you go ahead and try number 19. Now this is an exponential or logarithmic setup, but it's going to work the same as the trig. Rearrange this function, rearrange this integral so that it represents some known derivative, and reverse it. Okay. So now that you've had a shot at that, what you're going to be looking at is we're going to look through and we're going to say, hey, we notice that the derivative of e to the power is going to be e to the power. So all I need to do is get rid of that negative sign. So if I say negative integral of e to the x dx, I know that the integral of e to the x is e to the x, and I'm just going to keep that negative sign around, and there we go.